So if you watched my last video, which I know you did, you've learned about the shape of orbits and their changing speeds, but what if we have multiple orbits of different size around the same object? How do we relate them to each other? Well, lucky for us, Kepler made a third law while he was at it, and it explains Saturn's rings, satellite TV, and the brightest objects in the universe. But we're getting ahead of ourselves. Put simply, Kepler's third law says that small orbits are faster than wider orbits. More specifically, it says that the square of an object's orbital period is directly proportional to the cube of the orbit's semi-major axis. Now, if that meant nothing to you, don't worry, because we're going to define terms. An orbital period is just the amount of time it takes an object to complete one full orbit, and time, or t, is equal to distance over speed. The semi-major axis is half of the distance across the widest point of an ellipse. In a circle, that just means the radius, or r. So t squared is proportional to r cubed. We can transform this by saying that r is proportional to t raised to 2/3, or that t is proportional to r raised to 3/2. It's still very confusing why these numbers are what they are, so let's compare them all using a graph. We'll use the semi-major axis, radius in this case, as the x-axis and compare all the other values at different distances from a planet. In any orbit, gravity acts as a centripetal force on a satellite, and because it is the only force in action, it will be equivalent to the satellite's centripetal acceleration. So if we calculate the centripetal acceleration from the speed and distance according to the law, will it match? The law tells us that the orbital period is proportional to r raised to 3/2, and we know that the distance around the orbit is proportional to r. Speed is just distance over time, which gives us this curve. If we plug the values from v and r back into our acceleration formula, we get numbers that line up exactly with our predictions based on gravity. Kepler's third law really does predict stable orbital speeds at any distance. Let's apply this graph to reality for a moment. Think about Saturn. We usually imagine its iconic ring system as an integral part of the planet, but the rings are really just millions of ice chunks orbiting Saturn, disconnected from the planet and from each other. The total ring system is made up of countless concentric circles, each with a different radius and, therefore, orbital speed. We can't easily see this difference because of the ring's uniformity, but if we drew a straight line right across all of the rings, we'd see the inner rings steadily outrun the outer rings, forming a beautiful, mathematically poetic spiral pattern. The speed difference between orbital rings doesn't affect Saturn too dramatically, but consider what would happen if we stepped up the gravity a ton. The slope of the speed graph would get much steeper, meaning there's a sharper difference in speed between the rings. And when two rings are moving at very different speeds, they begin to generate friction. The most extreme cases of gravity in the universe belong to black holes, many of which intake matter in the form of ring-like accretion disks. The frictional difference between rings in this disk is so intense that it can generate light and heat on a level that puts entire galaxies to shame. Super bright accretion disks like these are called quasars, and they are the brightest sustained objects in the universe, all because of Kepler's third law.
Now, most of us live on Earth where gravity is a little bit more manageable. And since we probably won't visit a quasar anytime soon, let's bring things back down to our own system for a minute and talk about Earth's two brightest satellites, the International Space Station and the Moon.
They orbit in the same direction, but from Earth's surface they appear to go in different directions, the ISS speeding across the night sky in just minutes, the Moon falling behind Earth's rotation with all of the stars. This provides us with a great chance to demonstrate the accuracy of Kepler's third by comparing two very different satellites. The Moon is about 57 times farther away from Earth's center than the ISS. 57 cubed gives us 185,000, the square root being about 430. If we divide the Moon's orbital period of 28 days by 430, it gives us 1.56 hours as the estimated and surprisingly accurate orbital period of the ISS. Kepler's third law tells us that there is some distance from a planet at which any orbital period is possible. For Earth, we've applied this in a very practical way by finding the exact altitude where satellites orbit once every 24 hours, the same time it takes for Earth to complete one full rotation. If we position a satellite at this altitude above the Earth's equator, moving the same direction as Earth's rotation, it will stay centered over the exact same point on Earth permanently in what's known as a geosynchronous orbit. Satellites in geosynchronous orbit can maintain a direct, unchanging line of sight with all the same points on Earth, and this makes reliable communication paths possible. Like 22,000-mile-high network towers, Geosynchronous satellites enable sat phones to work anywhere in the world, along with satellite TV, radio, and much more. If we could see geosynchronous satellites from Earth, which we can't, they're way too far away for that, they would appear to hover in place above us, not moving at all from our point of view. Of course, they still move very fast, and so do we as Earth rotates beneath us. But our position on Earth makes a lot of concepts seem counterintuitive. Just from what we could see, we would never guess that the ISS and the Moon orbit the same way, or that Saturn's rings spin at different speeds, because none of us have been able to leave Earth and look at our solar system from a new, outside perspective. Some things we just can't observe directly. But as it relates to science, mathematical principles like Kepler's laws help us to understand what we cannot see. This video was researched, written, directed, acted, and animated by yours truly, Joe Somerville. Also, a special thanks goes out to Will Stephanie for designing and building this awesome contraption that physically demonstrates Kepler's third law in motion. It may be a little bit jittery, but what can you expect when we're not in space? Anyway, I hope you enjoyed this snack, and I'll see you next time.